Okay, welcome back, students. 7.2, general results for eigenvalues and eigenvectors. Okay. Results for eigenvalues and eigenvectors. The definition. B, an n by n matrix with eigenvalues lambda I. Lambda I at EI EI denote the set of all eigenvectors associated with lambda I. Okay, EI is called the eigenspace. Is called eigenvector of A corresponding to lambda I. Okay. Okay, so if we have times R times V1, V2 equals lambda times RV1, RV2. Okay, then RV1, RV2 are a family of vectors. That would solve, that would be eigenvectors. Okay, it's a family of vectors. Okay. So EI, or the eigenspace corresponding to a certain lambda, certain eigenvalue, okay, is the solution set to A minus lambda I, times V is equal to 0. Or we could call it the kernel of A minus lambda I. Number 1, find all eigenspaces of A equal to 3, -1, -5, -1. Okay. 3, -1, -5, -1. Okay. So let's find our eigenvalues first. Okay, so find my eigenvalue. I'm going to go lambda, -5, and then -1 minus lambda. Okay, and I'm going to set that equal to 0, 0. And then I'm going to solve. Actually, I'm not going to set it equal to. I want to find the determinant of this thing. So when is the determinant of 0? Okay, so let's find times -1 minus lambda minus -5 times -1. Okay, so 3 minus 3 lambda. Okay, and plus lambda squared minus 5 is 0. So I get lambda squared minus 2 lambda minus 8 is equal to 0. So lambda is equal to -4. Whoops. So lambda minus 4 minus times lambda plus 2 is equal to, so lambda would be equal to -2. Lambda 1 is equal to -2. And lambda 2 is equal to 4. Okay, so those are my eigenvalues. Okay, so for lambda going -2, we're gonna find out what the eigenvectors are. Okay, and we're gonna find out what the eigenspace is. Okay, the family of vectors. That would be a solution. Okay, so very similar to what we did before. Just in this case, we're gonna go 3 minus lambda, which is -2. Okay, -5, -1, and -1 minus lambda, which is -2. And then create an augmented matrix, setting it equal to 0. And I will get 5, -1, -5, and +1, 0, 0. So we can see that the second row is just a multiple of the first one. So this is going to this is going to reduce in one step to 5, -1, 0, 0, 0, 0. So for lambda 1, we would have 5. I'll call this A1. Okay. For V1, V1 will be A1, A2. A1, A2. Okay, so 5A1 minus A2 is equal to 0. So if I toss A2 to the other side, I get A2 is equal to 5A1. So I'm going to let A2 equal R. That means A1 would equal 5. Let A1 be equal to R. So that means A2 is equal to 5R. So instead of, factoring out the, well, we could factor it out. Instead of, factoring out the R from these, okay, I'm just going to say, look, that's my family of values. Okay, where R is any real number. Okay, and so one is my eigenspace, which is equal to V, okay, which is an element of R2, okay, such that V equals R times 5, R and 5R, where R is an element of R. And we could factor out the R if we wanted to. I'm just going to kind of leave it like that for right now. Okay, for lambda equals 2, lambda 2 is equal to 4. Right, it was 4. Yep. Okay, lambda 2 equals 4. Let's look at what we get. We're going to get 3 minus lambda. 3 minus lambda. Okay, negative 5. And then we get 1 there. And then we would have a negative 1 minus 4. And we want to find out, yeah, what does this thing, for what values? Okay, we'll let V2 be equal to B1, B2. Okay, let V2 equal B1, B2. And so for what values is this? Okay, is this going to be a solution? So this is going to become negative 1, negative 1, negative 5, negative 5. Okay, 0, 0. Okay, and I could actually make this into, if I multiplied the top by negative 5 and added, I would cancel out the bottom row here. And so this becomes negative 1, negative 1, 0, 0, 0, 0 in one step. Okay, I could also multiply through the top by a negative. And that would get me 1, 1, 0, 0, 0, 0. Okay, so what does this tell me? It tells me that B plus B2 is equal to 0. Okay, that tells me that B1 is equal to negative B2. So if we let B2 be equal to say S, okay, then B1 is equal to negative S. And so we could say eigenspace 2 is equal to, okay, all the values for V2, okay, such that, which is an element of R2, E2 is equal to negative S, okay, where S is an element of R. And we could factor out the S if we wanted to as well. But it's not essential, necessary in this case. Okay, look. Okay, let lambda I be an eigenvalue of A of multiplicity Mi, and let EI corresponding eigenspace, then a couple of things are true. Okay, one is a subspace of the complex numbers, okay, of n, okay. And then dimension of EI, lowercase, dimension of EI okay, is less than or equal to the multiplicity. Okay. Okay, so let's look at an example here. If I have an matrix 3 by 3, okay, 3, -1, 0, 0, 2, 0, and -1, 1, 2. Okay, my characteristic polynomial, okay, P lambda, okay, that's the determinant of this thing here. You know, the determinant of A minus lambda I, okay, okay, the characteristic polynomial would be 2 minus lambda squared and then 3 minus lambda. So we would say that this 2 minus lambda has a multiplicity 2. Okay, so we want to find all eigenspaces and their dimensions. Okay. Okay, so for lambda 1 equaling 2, okay, we have kind of a multiplicity because what we would end up doing is setting this thing equal to 0, and we have multiple root here, basically. Okay, so this has a multiplicity 2. Okay, so let's look at let's look for the eigenvectors here. So we would have, okay, along the diagonal, right? Remember, we're looking at the diagonal and we're going to subtract lambda from the diagonal. So we would get 3 minus 2. Okay, and then -1, 0, 0, and then 2 minus 2, 0, and then -1, 1 and then 2 minus 2. That would be basically, that would be a minus lambda I. Okay. And we want to set that equal to 0, or times v, sorry. We want this thing, v, v1, that equals 0. I'm going to do augmented matrix 0, 0, 0. Okay, I'm going to try to solve. This is going to be 1, negative 1, 0, 0, 0, 0, 0, row of zeros, and then negative 1, 0, and 0. Okay, and we can REF this. Okay, and we would get 1, negative 1, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. So we only have one row of non-zero entries. Okay, so okay, I could say that A1 minus A2 plus 0, 8, 8, 0. Now it doesn't matter what I plug in for A3. A3 could be anything I want. So maybe I'll call A3 T. Okay. Well, let's do R. Let's do S. Let's let A3 be S. Okay, and however, A1 and A2, okay, A1 has to equal A2. So if I let A1 be R, then A2 would also be R. Okay. So I get, okay, R, R, S. Okay, that's my vector. Okay. So I could say that my eigenspace for eigenspace 1 is equal to V1, which is an element of R3, such that V1, okay, is equal to, and I'm going to factor out, and I'm going to rewrite this as R times, okay, 1, 1, 0, plus S times 0, 0, 1, okay. Okay, and so E1 is really the span. E1 is really the span of these two vectors of 1, 1, 0 and 0, 0, 1. And since I only need two vectors to span E1, okay, this would have dimension 2. Okay, so the dimension of E1 is equal to 2, which is less than or equal to M1. And M1 was our multiplicity. And so multiplicity of 2, yes. So 2 is less than or equal to 2. Okay, so that checks. Okay, so my dimension was 2. Okay, and my eigenvector, sorry, my eigenspace is the span of those vectors, 1, 1, 0, 0, and 0, 0, 1. Okay. So one eigenvector would just be 1, 1, 0, and 0, 0, 1. So that would be one eigenvector, and then all the other eigenvectors would be any linear combination of those two vectors. You might even think of this as a basis. Okay, those two vectors are a basis, the building blocks for the eigenspace E1. Okay. For lambda 2 equals 3, which has multiplicity 1. Then I should end up with only one vector because the dimension of E2 should be 1. Okay, because I only have multiplicity 1. So let's look at this one. Okay, so we're going to have 3 minus 3, negative 1, 0, 0. Okay, and then 0, 2 minus 3, 0. And then negative 1, 1, 2 minus 3, and then 0. So equals, okay, 0, negative 1, 0, 0. 0, negative 1, 0, 0. So that's interesting. And then negative 1, 1, negative 1, 0. Okay. So I could do some row operations on this. And let's say that we do A 1, 2, negative 1. Okay, then that's just gonna get me a row of zeros in the middle. Up there. Okay, 0, negative 1, 0, 0, 0, 0, 0, 0, and negative 1, 1, negative 1, 0. Let's move some stuff around here. Let's permute uh, 1 and 3. Permutation of 1 and 3 would be negative 1, 1, negative 1, 0. And then 0, 0, 0, 0, and then negative 1, 1, negative 1, 0. Okay, let's permute or swap row 2 and 3. Oops, did that wrong. Should be 0, 0, 1, 0. 0, 0, 0, negative 1, 0. Okay. Let's permute 2 and 3. We get negative 1, 1, negative 1, 0, 0, 0, 0, 0, 0, negative 1, 0. Oops. Did it again. Gone too fast to permute this stuff. Okay, so this is going to be 0, 0, 0, 0 in the third row. Second row is 0, negative 1, 0, and 0. Okay. So let's continue on real quick. If I add rows 1 and 2 together, then I can kind of get rid of that of a 0 there. So this would be Okay, I'm gonna try to do RREF on this one. So just add 1, 2, 1. Okay. So we're going to get -1, 0, -1, 0, and 0, -1, 0, 0, 0, 0, 0, 0. Okay, and now I want to multiply row 1 and row 2 by -1. So multiply row 1 by -1 and multiply row 2 by -1, and we would come with 1, 0, 1, 0, 0, 1, 0, 0. Boom. So if we use b's in this case, plus 0 b2 plus b3 is equal to 0. Okay, so I know that b1 had to be equal to negative b3. Okay, but I do know that 0b1 plus b2 plus 0b3 is equal to 0, which means that b2 had to be equal to 0. So if I use t in this case, if I let b3 be equal to t, then I know that b1 is t, negative t. b2, come on. Okay, b1 is negative t, b2 it had to be 0, and b3 is positive t. Okay, so when I go to write my vector space, my eigenspace, I would get negative t, 0, and then t. Okay, I could factor out a t, that would be t times -1, 0, 1. So E2 is equal to V2, which is an element of R3. Okay, such that V2 is equal to t times -1, 0, 1. Okay, given that t is an element of R1. And so what is the dimension, what is the dimension of this guy here? Well, I only have one vector that could form a basis to create all of E2. And so we could say that E2 is the span, okay, of -1, 0, and 1. And so what's the dimension? What's the dimension of that basis? Well, there's only one vector. There's only one vector in that basis. So it's dimension 1. Dimension of E2 is equal to 1. Okay, which is less than or equal to M1, which was equal to 1. Okay, the multiplicity of, or sorry, M2, which is the multiplicity of that eigenvalue. Okay, the eigenvalue lambda 2 equals 3. Okay, so it checks nicely. Okay, let's go over some theorems here. Okay, theorem. Eigenvectors corresponding to distinct eigenvalues are linearly independent. A corollary of this. Okay, let E1, E2, E3, E4, to EK. Okay, be the eigenspaces of an n by n matrix A. Okay, in each eigenspace, okay, choose a set of linearly independent vectors and let S equal V1, V2, V1, V2, gosh, same thing twice. Okay, V2, there we go. Okay, dot. Okay, to V R. To VR. Okay. In each eigenspace, so in each eigenspace, we choose a set of linearly independent vectors and let S equal V1, V2 to VR. Okay. Denote the union of all of these vectors. So S is the union of all of those vectors in a certain eigenspace. Okay. Denote union of all of these vectors okay, then S is linearly independent. From example 2, it can be shown that the vectors V1, V2, V2, which is equal to 0, 0, 1. Okay, which were part of the one eigenvalue. Okay, we got two eigenvectors. Okay, because of the multiplicity that was involved. Okay, and in E1, okay, so these two were in E1. E1, and we ended up with vector. We'll call it V3. And V3, okay, equal to -1, 0, 1 in eigenspace 2, they are linearly independent. Okay, the set 1, 1, 0, okay, 0, 0, 1, and -1, 0, 1. Okay, 1, 1. Okay, this set. Okay, it can be shown that this set is linearly independent. Okay, we could see that by just looking at the vector as a matrix. Okay, REFing them, and we would get 1, 0, 0, 0, 1, 0, and 0, 0, 1. Okay. And so, okay, there, we, and so that is linearly independent. Okay, if I took the determinant of that, I would not end up with 0. I'd end up with 1. Okay. So it can be shown that it's linearly independent. Okay, definition. A has n linearly independent has n linearly independent eigenvector well, I should say that has, sorry. That has n linearly independent eigenvectors. If it has, okay, if there's no multiplicity, basically, if all of the eigenvectors are unique, okay, then it's called non-defective. Non-defective. And we say that A has a complete complete set of eigenvectors. A has less than n linearly independent eigenvectors. If A then n linearly independent eigenvectors is called defective. Okay, if A is non-defective, then any set of n linear independent eigenvectors of A is a basis for n, and it is called an eigenbasis. It is called an eigenbasis of A. Eigenbasis. An example two. Right? The 3x3 matrix has a total of 3 eigenvectors. Oh yeah, it does have 3. So it is okay if it has multiplicity. Okay, so in example 2, the 3x3 matrix has a total of 3 eigenvectors. Therefore, A is non-defective. Because the number of eigenvectors we ended up with was the same as the number of rows and columns of the original matrix. Okay. Therefore, A is non-defective. It also, what this says is that the vectors 1, 1, 0, 0, 0, 1, and negative 1, 0, 1 form a basis for R3. That's kind of cool. Not only is it a, well, not only do the first two vectors, they create a basis for the eigenspace 1. The last vector created a basis for the eigenspace 2, but the whole thing creates a basis for R3. Right. E2, I should have said. Okay, if an n by n matrix A has n distinct eigenvalues, Okay, so if it has indistinct eigenvalues, then we automatically know that it's non-defective. Okay. Then it is non-defective because each eigenvalue would have a corresponding eigenvector. And that would be n eigenvectors that would correspond back to n eigenvalues. It would be non-defective. That is all eigenvalues have multiplicity. Okay. Okay, and that's 7.2. I'll stop sharing and I'll see you in the next video. Okay.